Okay, welcome everyone. This is Professor Davis again, back to talk to you this time about molecular orbitals. I'd like to begin this discussion by considering two individual hydrogen atoms, which are depicted here as white spheres. Now, we already know from our discussions on atomic structure that each of these hydrogen atoms should have a 1s subshell containing a single electron. Now, the 1s subshell is really a probability density function of where we might find an electron located in space at any point in time. They don't really move in circular orbits the way I've shown them here, but this is the easiest way to convey that the electrons are in motion within that volume of space. Now, when these two hydrogen atoms get together and form a chemical bond, something happens to those 1s subshells. They merge and form what's known as a molecular orbital, or more accurately, a molecular orbital system consisting of two different regions of space. The first molecular orbital is called the sigma molecular orbital. You'll notice that the sigma molecular orbital contains a great deal of density between the two nuclei, and therefore electrons which may populate this orbital are likely to be found in between the two positively charged nuclei, screening them from one another and thereby stabilizing this molecule. The second molecular orbital which forms in this system is known as the sigma star. You'll notice immediately that the sigma star molecular orbital contains very little electron density in between the nuclei. And in fact, placing electrons in this location in space does nothing to stabilize the molecule. If anything, it actually will destabilize the molecule by pushing the two positively charged nuclei closer together through electrostatic repulsion. So when we work with molecular orbitals, we need to keep a few rules in mind. The first is that the number of atomic orbitals which go into the system is equal to the number of molecular orbitals which are formed. The second rule, molecular orbitals fill from lowest to highest energy following Hund's rule and the Pauli exclusion principle. And finally, bonding between any two atoms will only occur when there is an energetic advantage to populating the molecular orbital system when compared to the atomic orbital system. So now that we have a rough understanding of what molecular orbitals are and the rules that we need to follow to predict how they'll behave, let's take a look at some specific, simple molecules and see if we can explain their behavior using molecular orbital theory. So let's begin by considering the molecular orbitals of a hydrogen molecule, like the one that we looked at in the earlier slide. Here I've depicted on an energy diagram the atomic orbitals of two separate hydrogen atoms. Now, I've placed one electron spin up and the other spin down simply for convenience sake, but they could be in either orientation at this point. So let's take these hydrogen atoms and combine their 1s subshells to form the new molecular orbital system. You'll notice that in doing so, I've created the sigma molecular orbital, which is of lower energy, and the sigma star molecular orbital, which is of higher energy. So as I populate this molecular orbital system, using my allocation of electrons from my atoms, I'll begin with the sigma and only fill the sigma star if needs be. As you can see, I use my entire allocation of electrons in filling the bonding orbital. So in this case, the energy of the system overall has decreased. This means that there is an immediate energetic benefit to bonding. Furthermore, I can calculate the order of the bond simply by taking the number of bonding electrons, subtracting the number of antibonding electrons, and dividing by 2, of course, to acknowledge that there are 2 electrons involved in each chemical bond. So in this case, I have 2 bonding electrons in the sigma molecular orbital and 0 electrons in the antibonding sigma star. Placing these numbers into my equation allows me to predict that my hydrogen molecule will be joined by a single bond. And this is in fact the case. Now let's take a look at another example of a very simple molecule. In this case, we're going to work out the molecular orbital systems of a helium molecule consisting of H2. Now we all know that this isn't really how helium behaves, and what we're going to do now is demonstrate that there's no benefit for a helium atom to bond. So we have our 1s subshells on our energy diagram, each populated with 2 electrons, just as a neutral helium atom should be. Let's create that molecular orbital system now. There's my sigma and my sigma star molecular orbitals. But now if I populate them following Hund's rule and the Pauli exclusion principle, going from lowest energy to highest, what I notice is that while I place 2 electrons into a bonding orbital, I am forced to place my other 2 electrons in the higher energy antibonding orbital, canceling out the energetic benefit. This is easy to see in my calculation of bond order, in which I have 2 bonding electrons, but also 2 antibonding electrons canceling them out. Therefore, the net bond order is 0, meaning my prediction is that helium atoms will not bond to one another to form a diatomic molecule. So now that we've looked at 2 very simple examples, we're ready for something a bit more complex. Let's consider the molecular orbitals of a nitrogen molecule, N2. We all know from our discussions on atomic structure that a nitrogen atom should have an electron configuration of 1s2, 2s2, 2p3. It is the 3 electrons in the p subshell which will be participating in bonding during this discussion. So let's place that 2p subshell in our energy diagram and populate them as they would be in nitrogen atoms. Again, in this case, I place certain electrons spin up and others spin down simply for convenience. They could be in either spin orientation at this point. Now let's combine our 2p subshells and see what happens. You'll notice that when we do this, we get the expected sigma and sigma star bonding and antibonding orbitals, but we also have the possibility of pi bond formation now. The sideways overlap of the 2p orbitals from our 2 atoms create 2 pi bonding orbitals and 2 pi star antibonding orbitals of equal energy. Now let's populate this system using our allocation of electrons from our nitrogen atoms. You can see clearly in this case that all of the electrons have made their way downhill energetically into bonding orbitals. And furthermore, I can calculate the bond order of nitrogen molecule in the usual way. I have 6 electrons in bonding molecular orbitals, 0 electrons in antibonding molecular orbitals, meaning that when I run my calculation, I can predict nitrogen will have a triple bond. And of course, this is the case. Finally, let's take a look at one more example. How about a molecule of oxygen? Oxygen atoms have an electron configuration of 1s2, 2s2, 2p4. So we'll treat them similarly to the nitrogen example, except that each of our subshells now has 4 electrons. Just as before, I'll create my molecular orbital system by combining all of my 6 p atomic orbitals to form 6 molecular orbitals. As I populate them, notice that I have 6 electrons moving into bonding orbitals, but that I'm left with 2 additional electrons with nowhere else to go except into an antibonding orbital. You'll also notice that because I'm following Hund's rule and the Pauli exclusion principle, these 2 electrons go into individual pi star orbitals. The consequence of this should be clear, that the bond order of oxygen is determined by its 6 bonding electrons, but also its 2 antibonding electrons. Therefore, we would expect the bond order in oxygen to be 2. Not only that, but we expect oxygen to behave as a paramagnetic species because it contains 2 unpaired electrons in its antibonding molecular orbitals. And both of these are in fact the case with oxygen. And this concludes our discussion of molecular orbitals for now. I'll see you on the next installment.